Okay, well, thanks for being here at this colloquium. This iteration of the colloquium, we have Matthias Aschenbrenner from Vienna. So Matthias received his PhD in 2001 from the University of the United States and had positions at Berkeley, Chicago, and Los Angeles before moving. This is correct. In 2018, he received a prize from the Association of Symbolic Logic, jointly with Magna and Hoeven for their work on the model theory series. And today he's going to tell us about analytic hierarchies.
All right. Thank you. Thanks for coming, and thank you for the invitation. It's very nice to be back in Pisa. Let me get started. So I want to talk about analytic Hardy fields, but I think it might be useful to explain a little bit some of the history where this came from. So I'm going back to the 19th century. Okay, so here's a very classical question that people were concerned about at that time. So we all know, the familiar P series, the sum 1 over n to the P, which, as we know, converges when the P is bigger than 1 and diverges if the P is less than equal to 1. And, a big business in the 19th century when, calculus was first formalized was trying to find convergence criteria for series or also integrals. And a natural way to do so is to take a series like the P series, which you already know, is convergence or divergence behavior you already know. And if you have a given series, compare it with one of these series that you already understand. And well, people realized that, okay, there's something a little bit more general than P series, namely these so-called Bertrand series, which are formed in the following way. So you fix some m and again a p, and then you form the series where instead of putting the n to the p in the denominator, you put n times log n, log n, so all the iterates of log up to m minus 1, and then the p's power of log m of n p. Of course, this sum makes only sense if the n is sufficiently big compared to the m, then you can again show that it has a similar convergence or divergence behavior as the original P series. Well, it's a nice calculus exercise. You can use a Cauchy condensation test, for example, to check this, to reduce it to the original P series. Okay. Oops. Yes. So yeah, I'm focusing here on series, but of course you can also do the same thing for integrals. So let me not talk about the integral part. I'll just talk about the series version. Now, okay, this of course seems very naive, that any series that you want to, whose convergence you want to investigate could maybe be decided by comparing it to one of these Bertrand series. But it took it took a proof, and so this was shown by Paul de Bois-Reymond in 1873. He showed that the answer is no. So this was a German mathematician with a French name. The set theorists claimed that Cantor invented the diagonal argument, but I think one can make a point that he did it first in the course of his proof, a little bit earlier than Cantor, a few years earlier. So let me, every talk should have at least one proof, so I will try to explain how he did it. Okay, so so he invented also some interesting notation, useful notation, which you might have seen before. So for functions defined on half lines towards plus infinity, f and g, f is dominated by g means that simply the quotient f over g goes to 0, and f and g are asymptotic should mean that this limit exists, but it's a real number which is not 0. This, seems like a natural thing to do. Here are some examples, right, to get a feeling for this. So for example, this gives you an order of growth of the functions. For example, log x grows much slower than x, as we know. it's much slower than e to the x, and e to the x is dominated by e to the x, etc. But of course, this is not a total ordering on all such functions. Yeah, I mean, it's easy to come up with two pairs of functions. I gave you two here that are not comparable in either these ways. You know. Actually, this was one thing that bothered Cantor a lot. I mean, he didn't like this work of Dubon-Raymond, and the fact that this was not a total ordering really annoyed him. So. But I think nowadays we are used to partial orderings. Okay. So here is the theorem that he proved. So he showed that if you have continuous functions strictly increasing, so there's a whole sequence of them, which are decreasing in the sense of this dominance relation. So phi0 dominates phi1, etc. And they're all dominating 1, but that simply means they go off to infinity. Okay. Then you can find another continuous function also going off to infinity, positive, which grows slower than each one of these phi sub i's. Okay, so let me explain how this can be used to produce a counterexample to this convergence test, purported convergence test. So you define the following for an integer or natural number I and the real number p. You look at the function x log x up to the I minus first iterate of log, and then the ith iterate of log to the power p. Okay, and then you plug in p equals 2. It doesn't really matter, but any p that's bigger than 1 would be okay. So let me call this phi sub I. And then it's not hard to check that this is such a decreasing sequence. And you take an f as in the theorem. Okay. And you look at the series 1 over f of n. Okay, and now I'm not making a statement whether the series is convergent or not, but if it was, then you could not establish it with a comparison with the Bertrand series. Okay, because if it was comparable to a Bertrand series, for example, for some p bigger than 1 and some constant, right? So if the terms were eventually bounded by the general term of this Bertrand series, which is 1 over phi I p of n, well, then going to the next I plus 1, throwing in 1 more iterates of the log, you would get that phi I plus 1 of n divided by fn is bounded above by phi I p of n divided by fn, and by the choice here, this would be bounded by c. So this would mean that this fn would not be growing slower than all these, not growing slower than phi I plus 1. So this would contradict the choice of the f. Okay. So this is the theorem that he proved. So how did he prove this theorem? And this is where the diagonalization will come in a second. So to prove this theorem, it's convenient to dualize it. So instead of working with the phi i's, I'm going to look at the compositional conjugates. They will also go off to infinity. And then instead of the sequence being decreasing in dominance, it will be increasing in dominance. So I call these compositional inverses fi, and they will be increasing. And then what we need to prove is that there is going to be another continuous function which grows faster than all the fi's. Okay. All right. So this is what he showed. So how did he do it? Okay, he defined the following quantities. So the functions are defined starting at a. So we're looking at the following quantity m superscript n subscript I, which is the maximum of all of fi between this point a and a plus n. Okay. So this means that if I fix the I and I increase the n, then of course this sequence of maxima will be increasing. Okay. Now comes the diagonalization. You look at m superscript I subscript I, and you choose positive real numbers epsilon I, such that the sum of these multiplied by epsilon I converges. Okay, you can certainly can certainly do this. Okay, but then it turns out that if I replace here the I by some n, then this sum will also converge, okay, because I can break up the sum overall I into a finite sum from I equals 0 to n, and then the rest. But the rest is, every entry here is bounded by MII. So this is a tail of this infinite series. So in total, you have a finite sum plus an convergent infinite series, so you get something convergent. Okay, so this always, even if you put an n here, will be finite. Okay, but now, using this, you can easily see, because this is now for every n, that if you look at the sum of this infinite series of these functions, epsilon I, fi, then on each bounded interval from a to a plus 1, this will converge uniformly because of this, what is called the Weierstrass M-test, which we just verified. So this means this will converge to a continuous function, okay, defined on the whole half line. And because everything is positive here, this infinite sum will be greatly equal to every entry, every summand. And the fn plus 1 are increasing in dominance. So this means that this function here will dominate every one of the fn's. Okay, so this is the continuous function that we were looking for. Okay, so this was my proof. So from now on, there will be not be any proofs. Okay. So now you can, once you know this, then it's of course interesting to wonder about the various refinements of this. How far can you push this method? Okay, so it's not too difficult to modify this argument. I mean, instead of taking just the supremum, you take the supremum, and you also let take the diagonalize against the derivatives, so to speak. So if all the fi's are of class C infinity, then you can choose the epsilon I so that this infinite series that you produce will also be a smooth function. So this is not a big deal. You can also wonder, okay, so now I had in my example here, I had one sequence of functions that were growing faster and faster, and was finding a function that was growing even faster. But what if I had also a condition on the top? Yeah, so if I have some g's, which give me a condition on the growth, so I want a function that grows faster than all the f's, but not too fast. Okay, and then indeed you can also find such an f. So this was shown by Adama. But there are also some further strengthenings that you can wonder about. So, for example, in the first case, right? So, if all the f's there are C infinity, can you choose this C infinity function f that you produce in such a way that not only does it dominate all the fi's in the sequence, but their derivatives also dominate all the derivatives in the sequence? Okay, so this is one thing you can wonder about. Another question is, of course, can you strengthen this not just to C infinity, but also to analytic? And the answer is yes, at least in the first case. So this was shown by Poincaré. You can always choose this f here in this first situation here to be analytic. Okay, so you can find analytic functions that grow extremely fast. Yeah, so I mean, these fi's could be the iterates of the exponential function. So yeah, computers extremely fast growing analytic functions. Okay, but then you can also ask, okay, what about the second situation, right? If I have an upper bound, can I also find an analytic function that does both? Okay, and what I want to show in this talk is that these last two refinements also have positive answers, at least if you assume that these f's and the g's lie in what we call a Hardy field. Okay, and this is what a Hardy field is. Okay, so in a nutshell, so according to Rosenlicht, these are the natural domain of asymptotic analysis, where all the rules hold without any side conditions. Okay. Now, of course, this comes at a price, because it means that you have to restrict the kinds of functions that you allow very much. Okay, so okay, but they are still useful. I mean, this is still a rich enough class to contain interesting functions, interesting in mathematics. So one can view them as a sort of a baby version of what people know as ominimality, which is a subject which has seen a lot of interest recently, because it is so useful for applications even in fields like number theory. But Hardy fields themselves have been used also in other subjects like ergodic theory. So my plan is to first explain what a Hardy field is, and then explain some transfer principles. So this is the logic part, which have to do with Hardy fields, and some of the recent improvements that we have, which look a little bit innocuous, but in fact are very powerful. So I will state some rather unexpected consequences of these improvements, and then in the end I'll also pose a few questions. Okay, so, okay. Yeah, and I didn't say this before, but all of this is, joint work with at least a subset of these people, Lau, Dries, and Joris van der Hoeven. Okay. Okay, so let me explain what Hardy fields are. So first, I need some notation. So for every natural number r, I let c to the r be the ring of germs of r times continuously differentiable functions defined on some half line towards plus infinity, real valued functions. So what are germs? Well, this means we identify two such functions if they agree on some potentially smaller half line, okay, towards plus infinity. So in other words, we're only interested in the behavior of the functions towards plus infinity. And this is naturally, in a natural way, a ring, commutative ring, right? Because you can define addition, multiplication pointwise on the germs, and it's almost a differential ring, right? I mean, if you take a derivative, you can also define the derivative pointwise, but then from CR you land in CR minus 1. Okay. So to get an actual differential ring, so in other words, something that is closed under taking the derivative, you take the intersection of all of them. Okay. All right. Now, we denote this by c to the less than infinity. And this is a little bit subtle. Okay, so there is also a differential subring consisting of the smooth function. So these are those germs which have a representative defined on some half line, which is actually C infinity. If you're in this intersection, right, then for every R you have a representative that is CR. But as the R increases, you might have to make the half line smaller. Okay, so we have this differential subring C infinity, and then there's also C to the omega. So these are even smaller, the ring of germs of analytic functions eventually. Okay, and then the definition of a Hardy field is simply that this is a differential subfield of this ring, differential ring C to the less than infinity. And the emphasis here is on field. Okay, so it's not just a subring, but it's actually a field in the sense of algebra. Okay. And then, okay, in an analogous way, you can also define C infinity Hardy fields or C omega Hardy fields, right, by looking at differential subfields of C infinity C omega. And in fact, okay, we have, of course, natural inclusions. Every C omega Hardy field is a C infinity Hardy field, and each one of those is a Hardy field. But all these inclusions are actually strict, but it takes a bit of work to come up with explicit examples. Okay, so I'm not going to give the examples, but there are examples. Now, here are some easy examples. Okay, so for example, if you have a constant function, right, all the constant functions, or the terms of the constant functions, well, they form a Hardy field, namely R, because if you take well, it's a field, obviously, but if you take a derivative of some constant function, you get 0, so it's closed under the derivative. So something more interesting is if you take the rational functions. So what do I mean? Well, these are the terms of the rational functions with real coefficients. Why is this contained in C less than infinity? Well, this is essentially because if you have a rational function and you substitute into the denominator, well, this denominator has only finitely many zeros, so at some point it will be non-zero, and this expression will make sense in the world of terms. Yeah, so x here denotes the term of the identity function. And of course, it's closed under taking the derivative. Yeah? So here we have an example of a Hardy field. Okay, and then similarly, you can make this a little bit bigger by also throwing in a function that grows much faster than x, like e to the x, or something that grows slower, like log x. Yes? Well, analytic simply means the same thing, except that you put the ring of terms of analytic functions here. Yeah, so, and all these examples here are analytic. Okay, so in fact, most of the Hardy fields that you meet in practice are going to be analytic. So this is why in this talk I want to focus on those. Okay, so this is this small class here. Okay, so now to give you a little bit of a feeling, I'll give you more examples in a second, but to give you a feeling, let me explain what these axioms of Hardy fields imply, because they are very strong. Okay, so let's say we have a Hardy field H and we have some element F in H. Okay, so what does F not being equal to 0 mean? Okay, so this means as a germ, right, this is not equal to 0, so it's not eventually equal to 0. Now, because H is a field, this means there has to be a multiplicative inverse. So 1 over F has to be in H, okay? But this means that F cannot be infinitely oscillating, right? It has to make up its mind what its sign will be. Okay, so it's a sign, because we're dealing with terms of continuous functions. Yeah, so I'm not distinguishing here between the terms and the representatives. I always write F. But this means, yeah, so that if F is not ultimately equal to 0, it means that eventually it is positive or eventually it is negative. So this is what I meant before, right? I mean, you have to exclude oscillating functions. Okay. But as a consequence, because of this observation, you can define an ordering on any Hardy field. Okay, you can say that declare a function to be positive if it is eventually takes on eventually. So it can declare a term to be positive if its representative or any of its representatives is eventually positive, and this defines then, you know, a total ordering on the field, making this an ordered field in the sense of algebra. So the ordering is compatible with plus and times. Okay, now this observation that we did here applies not just to F, but also to the derivative of F, because H is closed under taking the derivatives. So if you have an F like here, F prime, well, it could either equal 0. This would mean F prime is eventually equal to 0. This means F is eventually constant. Or if it's not 0, then it's eventually positive or eventually negative, right? So this means that F is eventually increasing or eventually decreasing. Okay, so this means F is eventually monotonic. And this means that the limit has to exist as a real number in the extended real line. So okay, so you can see that the Hardy field axioms have some very strong consequences right there. Moreover, these asymptotic relations of Dupont-Raymond actually are total in a Hardy field. So if you have terms in a Hardy field, one of these relations will always have to hold. Okay. Yeah, there's a slight variation of this, which was maybe defined by Hardy, not by Dupont-Raymond, but you can also define a weak relation. So F is weakly dominated by G. Well, in the O notation, this means F is big O of G. And in the Hardy field, this simply means that f over g goes to a real number. So, well, I gave you two other ways of expressing the same thing. So we use all these three relations. And here is a little example of what Rosenlicht meant, with no side conditions. Okay. So suppose you have two terms f and g non-zero and not asymptotic to 1, living in the same Hardy field. Then f is weakly dominated by g if and only if f prime is weakly dominated by g prime. Okay, so you can differentiate and integrate on both sides of such an asymptotic relation. And really what this means is, okay, if you think about it, what this means, right? So f weakly dominating g, so this, if you bring the g to the left-hand side, means f over g is dominated by 1. So this means that f over g goes to a real limit. And this means f prime over g prime also goes to the real limit. Okay, so this is a version of L'Hopital's rule. But with L'Hopital's rule, you always have to be careful. Okay, there's always these examples in calculus when you teach your students, right? There are side conditions. You need to know that the limit of f prime over g prime exists, right? For you to claim that the limit of f over g and f prime over g prime is the same thing. But here we don't need to say this because f prime over g prime always has a limit because f prime and g prime lie in a Hardy field, and we don't run into this problem. Okay, so okay, yeah, and then for the people who know, if you look at the set of elements which are weakly dominated by 1 in a Hardy field, they form a valuation ring of this field. And this is a certain type of subring which has only one maximal ideal. And these are exactly those elements in the Hardy field which are strictly dominated by 1. So this means they go to 0. Okay, so I kind of think of them as infinitesimal because the limit is 0. So you can draw a picture maybe of a typical Hardy field. So you think of this as sort of an extension of the real number line. So here we have the real numbers, but then beyond that we have the terms of functions that go to infinity, like log x, e to the x, e to the 2x, right? They live out there, and similarly to the left if they go to minus infinity. And then the things that are bounded by 1, well, these are the things that are within the convex hull of the real numbers. So this is the O. And then the little o, well, this is sort of the monad around 0, all the things that go to 0. So this means that they're ultimately smaller than every real number. And this is one way to think about what the Hardy field looks like, some extension of the number line. Okay, so yeah, here are some examples of functions that do live in Hardy fields, which are interesting. So for example, the error function, okay, which is depicted up there. But also maybe more interesting is, so there are the Airy functions. There are solutions of this linear differential equation. So there are some particular solutions which form a basis, the Airy and the B-Airy function. And note their graphs, okay, because I'm not looking to the left, I'm looking to the right. And to the left they're oscillating, but to the right they are nicely behaved. And this is in fact a behavior that have with very many special functions. Even on the complex plane, I mean, there are some directions, if you look in this direction, then the behavior of the function is horrible, it's oscillating. But if you look in some other direction, then the function lives in the Hardy field. And this is a very typical thing. Okay, now these examples are, they all satisfy differential equations with the real coefficients. But the last example here is slightly different. So this is the gamma function. Again, looking towards plus infinity. And there's a theorem of Hölder which says that this does not satisfy an algebraic differential equation with real coefficients. So it's slightly different nature. Okay. Okay, more examples of Hardy fields. Now there's a whole machinery now with which one can produce Hardy fields, but historically it started with, the name came from Hardy because he kind of made sense of this work of de Bournemont, and he showed in particular that the logarithmic exponential functions or their germs form a Hardy field. So what are those? Well, these are the functions that you can get infinitely, what are germs, infinitely many steps, starting from the constant functions, the germ of the identity, the algebraic operations, exponentiation, and logarithm. Okay, so you can build up these functions, and he showed that the sign of every such function is eventually constant, and hence they form a Hardy field. Okay, here are some examples, right? Easy examples of LE functions. I mean, my iterations here are not very deep. So e to the x plus x squared, for example, but also I think like this would be an so-called LE function. Okay, but this is still a very small Hardy field. I mean, for example, it's not closed under integration. Okay, so taking antiderivatives takes you out of this. Okay, yeah, I mentioned the connection to ominimality. So there's a way of associating to an ominimal structure on the real field a Hardy field. Okay, so this gives you a wealth of more examples. Okay, so people now have very sophisticated ways of producing ominimal structures, and then whenever you do that, you have as a bonus, you get a Hardy field. And yeah, I don't want to explain too much in detail how this goes, but here's one example. Okay, so if you look at the Hardy field that's associated to the ordered field of real numbers itself, you can give a very explicit description of it. Namely, these are simply all those terms which are algebraic. So in other words, which satisfy an algebraic equation with rational function coefficients. Okay, so that is a Hardy field. Okay. All right, so now how do you construct new Hardy fields from old ones? Well, a general way to do this is try to solve a differential equation, analyze this solution, and hope to adjoin it to a Hardy field that that you already have. So a systematic way to do this is, okay, you take a polynomial. So H is my Hardy field, my given Hardy field. I take a polynomial in the variables y, y prime, y double prime, etc. Non-constant polynomial. And then ask, okay, well, if I want to solve this equation, okay, I simplified it here a little bit. Instead of p of y, you should think of p of y, comma y prime, comma y double. Substitute the derivatives. Right, so I can ask, okay, when is there a y in some bigger Hardy field that solves this equation? Can I do this? And yeah, I mean, in the 20th century, there were a lot, so there was some work by various people answering this in specific situations. So names to mention here are Hausdorff and Hardy in the early days, and then Bourbaki after World War II, and then in the 70s and 80s, Rosenlicht and Bojanitsyn did a lot of work on these issues. So here's one example of a theorem that one can prove. So what's the first, the easiest kind of differential equation that you might want to consider? Well, order one linear differential equation. So you look at the equation y prime plus fy equals g. F and g are my given functions in a Hardy field H. And then actually it turns out that any solution to this equation, okay, is actually contained in a Hardy field that contains the given Hardy field H. Okay, well, special cases, right? So special case would be if the f and the g are 0. So you look at the equation y prime equals 0. So what I'm saying here is that I can always adjoin any constant. I didn't, explicitly require that all the constant functions are in H, but I can also throw them in. So I can always adjoin any constant function. Also, I can always adjoin X, because X satisfies the equation X prime equals 1. So I can always adjoin X to a Hardy field. But then, other things I can get using these order 1 equations. Well, I can get antiderivatives. Okay, I said the LE functions are not closed under antiderivatives, but I can always throw them in. And I can always exponentiate, and I can always take logarithms, at least if they make sense. Okay, so in fact, this is one way to show that Hardy's field of LE functions is a Hardy field, because he closes off under the algebraic operations, but also under log and exp. So, okay. Now, to simplify this kind of thinking, it's useful to focus on those Hardy fields that you cannot make any larger anymore. Now, the logicians know Zorn's lemma, right? So the axiom of choice will always give you a maximal Hardy field extension. So if you start with some H, just extend it until you cannot do it anymore, and that's a maximal one. Okay. So it's simply a tool to not having to say all the time, in some extension something happens. Okay, so I'll just now focus on maximal Hardy fields, those which cannot be extended anymore. Okay, so then what we had on the previous slide can be rephrased as saying that if you have a maximal Hardy field, it already contains all the real constants, because if there was a real constant that wasn't contained, I could have joined it. And similarly, it's closed under integration. It has to be closed under exponentiation and logarithm. And it is also real closed. That was not part of the previous slide, but it was a theorem essentially of Hausdorff. And one way to say this is in down-to-earth terms is that if you join square root of -1, you get something that's algebraically closed. Okay, so fundamental theorem of algebra. Okay, so what we now have is, since a few years, is a fairly complete understanding of this extension question for arbitrary differential polynomials, not just those simple ones, y prime plus fy equals g, for arbitrary differential polynomials. Now, I don't really want to explain the full force of this. I'll say a little bit later, but okay, to explain the statement, here is two things that one now knows. We call this the weak differential closedness. Okay, this will only make sense to the logicians, so the other ones should ignore it. But what this is saying that if H is maximal, well, it might happen that you cannot find a solution to a given differential polynomial, but you can always, if you go to this complexification. So if you go to this algebraic closure, H adjoint I, then there will always be solutions to algebraic differential equation. Yeah, this statement here means that it's real close, but this is about the differential polynomial, right? So it also involves derivatives. So you can always solve any differential equation in the algebraic closure. And if P happens to have odd degree, then you can actually always find a solution in H itself. Now, of course, this is very reminiscent of what happens with ordinary polynomials over the reals, right? I mean, fundamental theorem of algebra says if you go to the complex numbers, you can always find a zero, and if the polynomial is odd degree, you find one in the reals. Yes. Yeah, square roots exist, yeah. In particular, I mean, but this is already covered by this. Huh? But this is about the differential equation. So here's one example, right? So you write down some random differential equation with Hardy field terms, right? For example, e to the x log x gamma. I cooked up something here. It looks like a horrible differential equation, but the crucial information is that the degree is 5, which is odd, And then this means that if you take a maximal Hardy field containing all this stuff, then there will be a zero there. There will be a solution to this differential polynomial. Okay. So how do you show something like this? Okay, this is a long story. And essentially, it starts with first doing something similar in a context where we don't really deal with functions, but with formal series. Okay, which makes life easier because you don't have to worry about convergence and actually, doing analysis. So what we show is that every maximal Hardy field is what the logicians call elementarily equivalent to the differential field of trend series. These are formal series, often divergent, which are more complicated than power series. They involve exponential and logarithmic terms, and they can be used to model the asymptotic behavior of functions that live in Hardy fields. So for the examples that I had up on the board, I wrote down a few of these classical asymptotic expansions, and you can see that they are series that are not just power series in 1 over x, like here, but also involve exponential terms. Right? So here is for the Airy function. For the gamma function, it's even worse. I mean, I wrote it here for the logarithm, but yeah, you have log x, for example. So this series on the right would be examples of trend series. I don't want to give the formal definition of what this T is, but I think these examples should give you an idea of what trend series look like. They're formal series with real coefficients, and the monomials themselves are trend series, which are somehow simpler than the series. That's whose part they are. Okay, and yeah, this definition of elementary equivalence I don't want to assume. So let me explain what this means in the down-to-earth terms using systems of algebraic differential equations. So let's say we have a system, very general, if these differential polynomials, maybe now with several indeterminates, and I'm not just looking at systems of equations, but maybe I also have other relations that I want to require. Okay, and the coefficients of these differential polynomials are in the Hardy field, and I'm interested in whether such a system has a solution in H or not. Okay, and a strong version of this elementary equivalence is you can phrase as the following transfer principle: if the system has a solution somewhere in some Hardy field that contains H, then it will actually have a solution in every maximal Hardy field that contains H. Okay, so somehow these maximal Hardy fields are, although you construct them using Zorn, they are kind of indistinguishable in this sense. So yeah, here are two examples. I mean, here's one system of which you can show that it has no solution in a Hardy field. But the second system here, so this is a certain first order equation, not first order, but this kind of equation where there's a y prime is singled out here. This kind of equation has a solution in every maximal Hardy field. Okay, so sometimes things are even better. You can actually embed a Hardy field into this huge field of trend series. So such an embedding you can kind of think as an expansion operator, right? So I said that this trend series you should think of asymptotic expansions. So then if you have such an embedding, then you have a coherent way of associating an asymptotic expansion, which is compatible with the algebraic structure and also the derivation. And the inverse of such a thing you can think of as a kind of a summation, abstract summation operator. Somebody gives you a trend series and you're able to produce an element in the Hardy field. So there's one well-known example where there is such an expansion operator that you can write down, namely for the Hardy field that we saw before, the algebraic series. So there, you know that there is an expansion operator whose image in T are the real Pusey series, which are algebraic over the rational numbers. So that's a very concrete example, but most of the time, these images of the various H's are pretty complicated. Now, the advantage is if you embed an H into T, is that you can argue formally, because T, as I said, is a formal object. You don't need to worry about convergence. You can do all kinds of constructions and work more combinatorially, and then use this summation to go back. So here's one example. I looked at the Euler equation, y prime plus y equals 1 over x. So it's well known that the solutions look like this. Okay. And yeah, in T, you can formally solve this equation. Okay, y prime plus y equals 1 over x. You can formally solve it, and what you get is the Euler series, which is divergent, plus a constant multiple of e to the minus x. And how do you get this particular solution in the trend series? Well, you just write this equation as a fixed point equation, and this means you need to look at this operator, 1 over x minus f prime, and you'll find a fixed point of this, which you can do formally, and if you do it, then work out the coefficients, then you see that you get the Euler series. So you see that this is much easier to do in the formal world than in the world of germs. Okay. And then if you have such an embedding, there's also a transfer principle that relates solutions in H to solutions in T. So if you have an embedding, then you can apply this embedding to all the coefficients in the system. You get a system over T. And then there's a transfer between T and Hardy fields. And this was some of the key that we proved that because we already understood the algebraic differential equations that could be solved in T. And so we could, once we proved this transfer result, we knew what was going on in Hardy fields. So if this system that you map into T has a solution in T, if and only if the original system has a solution in some Hardy field. Yeah, and then there's a refinement. I mean, you can even choose the solution to live in a Hardy field that you can still, again, for which you again have a summation operator. Okay, and there are also smooth and analytic versions. So let's say you start with a smooth Hardy field and your system has a solution in some bigger Hardy field, which might not be smooth. Okay. But then in fact, there will also be a solution in a smooth extension. So in fact, each maximal smooth extension, maximal smooth means it's a maximal, it's not a maximal Hardy field that is smooth, it's a maximal smooth Hardy field, the maximal element in the category of smooth Hardy fields. This partial order. So then you will have a solution in each maximal smooth extension. And similarly for the analytic case. Okay. Now, the theorem I want to explain is that we proved a version of this which sounds innocuous, or a refinement which sounds innocuous, which is very powerful. Namely that if you have a Hardy field and two countable subsets, A less than B, then you can fill this gap that is built between these two countable subsets by some element which is in some Hardy field which is bigger than H. So phrased in the maximal Hardy field language, this means that they have the property of eta 1 for the people who know about what it says. Yeah, this first we were able to only do this in the usual Hardy field setting, and then it took a while to do this also in the smooth and analytic categories. In fact, in the analytic world, this was a little bit surprising to us, and this is what I want to explain. Yeah, just some special cases because these are related to the earlier stuff. So if you have a maximal, phrasing here the analytic version. So if you have a maximal analytic Hardy field, then it will always contain a trans exponential element, an element which grows faster than all the exponentials. So this is the special case where the B is empty and the A consists of these iterated exponential. Now this had actually been shown earlier by Bouchanitsan in a completely different way, using functional equations. In the smooth case, it was shown by Sjöden, some Swedish mathematician. Okay, but then you can also do this in the case where instead of the iterated exponentials, you look at the iterated logarithms, which go slower and slower, like we've seen those before, and you can find a g which is going to infinity, but going to infinity slower than all the iterated logarithms. So this is something that Bouchanitsan didn't know, apparently. And of course, this is obviously related. You know, these are generalizations of these facts that I mentioned earlier of Dubois-Reymond and Erbrandt and so on. Now, if you combine this with our earlier work, you actually get some logical consequences which are interesting. So the first one is that if you have two maximal Hardy fields, they will be what the logicians call back and forth equivalent. I don't want to explain what this means, but essentially it means that instead of systems with finitely many conditions, you also allow systems with countably many conditions. And using a little bit of set theory, this leads you to the astounding conclusion that if you have two maximal Hardy fields and you assume the continuum hypothesis holds, then not only are they logically indistinguishable, they are outright isomorphic. And the same, of course, also in the other categories. So all of these maximal objects will be very canonical. Okay. So I don't know how much time I have. I can't really. 5 minutes. Okay. So let me explain a few more applications, which show you that this class of analytic Hardy fields is actually surprisingly rich, and maybe a little bit too rich in the end. So they contain many order differential fields of a countable nature. Okay. So for example, as explained in the following corollary. So take one of these maximal analytic Hardy fields. Every Hardy field which is of countable transcendence degree over its constant field will embed into M. So you can always embed any Hardy field which is countably generated in this way into any given maximal analytic Hardy field. Okay, and even better, you can embed the whole field or the differential field of trend series into M. So you find a summation operator which takes values in this M defined on all the trend series. Now, I like to think of this as a sort of a Hardy field version of this famous theorem of Bezikovich, which in turn strengthened this theorem of Borel, which I think many people know. So that says that if you have a formal power series, any formal power series, there will always be a C infinity function defined, let's say, on the interval from 0 to 1, which has at 0 this formal power series as the Taylor series. Okay, and Bezikovich strengthened this by saying, okay, you can actually choose the C infinity function to be analytic away from 0. Okay, so it is on the open interval from 0 to 1. Let's say it's analytic. At 0, it's only C infinity, and it has this Taylor series. And this is the way to think that I think about this, right? So somebody gives you a trend series, right? And you find a germ of some eventually analytic function living in M, which has this asymptotic expansion. Okay, and yeah, what is the countability property in part 2 that's relevant here? It's okay, I'm not sure whether this is standard, but what I like to call the shortness of T. So every So this T also has a natural ordering, like a Hardy field. And every well-ordered or reverse well-ordered subset of T is countable. And this is some of the key countability property that's needed. Also, this T itself is huge. Yeah? It has this countability feature. Okay, yeah, here is an embarrassing question. I mentioned, so the maximal Hardy fields and the maximal analytic, maximal smooth. We don't actually know whether these things are different. Okay, so it could actually be that the maximal analytic Hardy field is actually already a maximal Hardy field. We don't know. But they're very close. I mean, any maximal analytic Hardy field turns out to be dense in the order topology in every extension. Okay. All right. So I have 2 minutes. I'll want to have 2 slides on the proof, then 2 questions. Okay. So the proof is a bit long, but the strategy essentially boils down to 2 cases. So you want to adjoin this Y, filling in this gap between A and B. And there are two cases. The first one is that you can approximate this Y by a Cauchy-like sequence, a so-called pseudo-Cauchy sequence, of elements in H. Okay, and this means that this Y will exhibit the same order of growth as an element of H. And the second case is where, well, this doesn't happen, and then you will introduce a genuine new order of growth. In the part 1, yeah, we could use some earlier results that we know, from this weak differential closeness business, some techniques that we had developed there, and also some analysis using partitions of unity and so on. But the part 2 was a little bit harder. It also splits into several subcases because we kind of know what happens. I mean, for the connoisseurs here, I mean, what happens on the level of the value group. We understand what. So this gave us a way of analyzing, splitting this up into further cases. This in particular is now literally this situation of Dubois-Reymond, where these FIs had different orders of growth, and we were trying to find an element with another new order of growth to fill in this gap. And the most difficult case involved certain Y's, which can be expanded in a sort of an iterative way, which I indicate here. And so they solve some sort of, I don't know, kind of functional equation given by a sequence of elements in the given Hardy field. And you needed to find such a Y. Well, first of all, you needed to find a solution to this at all, but also then one that lives in a bigger Hardy field. And this was a bit delicate. And curiously enough, it also involved at the very end a diagonalization argument. So that seems to be a feature of this whole thing. Okay, so this is in the case of the regular Hardy fields. I said that we didn't know it for a while in the analytic and smooth category, but for that there is a powerful tool, namely Witness approximation theorem, which everybody should know. Okay, this is just a baby version of it, but that's enough for our purposes. And it's really an astounding theorem. It says that if you have a C-infinity function on some half-line, in some error function epsilon, continuous, positive, then you can find an analytic G, which approximates f up to this error epsilon, but not only f, but also all the derivatives of f. Well, if at least you're willing to wait until the approximation kicks in. Okay, so the epsilon here, this is only the n here is bounded by 1 over epsilon of t. But if epsilon goes to 0, right, then 1 over epsilon t will go to infinity, and then for more derivatives, eventually this will hold. Okay, so we needed. It was not literally this that we needed. We needed a version for these terms. But that was not too hard to get from this theorem. And then once you have this version for germs, then you can use the earlier results where you can find a solution I fill in for the gap and then approximate it using this theorem by an analytic solution. Okay, and then there was one more slide which I'll skip, which is about a refinement of this, where you also try to keep track of the holomorphic extensions, but time is short, so I'll finish with these questions, which of course are quite natural, and whose answers I don't know. So we showed in the first one, right? So we showed that any two maximal Hardy fields are isomorphic if you assume the continuum hypothesis. Well, is this necessary? Okay, so could there be a model of set theory in which there are non-isomorphic maximal Hardy fields? I don't know. And another question is, so we have this order topology. We have to, could there be a maximal Hardy field which is complete? And in such a world, this maximal Hardy field would not be isomorphic to the differential field of serial numbers of countable length equipped with the derivation of Verraducci and Mantova. Yeah, it's almost a crime that I didn't mention serial numbers, but complete in the sense of the Cauchy sequences of arbitrary length in the order topology. Yeah.
Isn't the only complete field there is
no, well, Cauchy sequences with countable lengths, yeah, but arbitrary lengths. Yeah. Okay. Anyway, that's. Oh yeah, and I just warmed my heart. I mean, I walked. So thank you. It's pizza. Yes. They seem to like the mathematicians here. So. Yes.
So first, the original question that you mentioned at the beginning, so filling a gap.
Right.
You say that we can fill a gap if the sequence below and the sequence above belong to a given attribute.
Yes, yeah.
And what happens if they don't?
Yeah, if they don't, yeah, this is a good question. I never really thought much about this. I mean, I don't know. I mean, it's possible that this is somewhere in the literature, but I have not really thought about this. Yeah, so if you have arbitrary gems. I mean, it might even been discussed in Hardy's book. I mean, Hardy has a lot of these classical results about, also proof of this Dubar-Riemann theorem. Actually, a different proof here. He has a different proof.
The second question is for people who know the subject already. Can one say something about maximal H fields other than H fields?
Oh, well, this doesn't really make sense, right? I mean, because maximal, I mean, because the Hardy fields are all subrings of C less than infinity, right? So they're, yeah, yes. But there is, lurking in the background here is, of course, that we have this axiomatization of the theory of the differential field T, right? And so these are, H fields with certain closure properties, and what we show is that, maximal Hardy fields are also models of this. So from this comes this transfer principle.
I was curious about the continuum hypothesis result.
Mm-hmm.
So you use the saturation of the order, but the result.
Yeah, I mean, well, basically, once you have this back and forth system, I mean, then it's.
You're using the
Yes, I mean, we use the property of the order to construct a back and forth system, right? And once you have the back and forth system, it's the standard argument that, you know, well, more or less the standard argument to construct the isomorphism. Yeah. If you have the continuum hypothesis, then you will end up with an isomorphism. Yes, but
what's it is not a good question, but what's the sort of hunch about the existence of?
yeah, I think that probably one can construct these things. Yes, yeah. If one knows one's forcing, so, which I don't, but yeah, yes, I know. Yes. Well, okay, I mean, there is a topology, right? I mean, it's given by the order. I mean, the order. Oh, yeah. Yeah, it's a good question. I don't know. So you're basically asking for some closure and yeah, infinite summation in, for example, in the right way. Yeah. Yeah, it's a good question. I never thought about this. I mean, of course, in some sense, yeah. For example, with these pseudo-Cauchy sequences that we construct, I mean, you know, there's whose limits we construct. I mean, this is kind of this kind of thing. Yes, yeah. Yeah, yes, yeah. At least if you restrict to countable length sequences, yeah. Yes, yeah, that's a good question. Yeah. No. Yes.
What about closure of the composition?
Yeah, okay. I mean, I knew that you would ask this. I mean, I have this summation operator for the trend series, you know, but the analysts are not going to be impressed by this because it's okay. It works well with the algebraic operations and derivatives, but to make this really useful, it would be good if it could also work with composition. Yeah. But we don't even know that maximal Hardy fields are closed on a composition. So yeah, we have a problem. Yes, I don't know. This is all. I think there's still a lot to be discovered.
The question is then again.